Yeah, so hello everyone. Today we have Max Hubner, who will tell us about the holographic dual of a topological symmetry operator. Max, take it away.
Thank you, Laksha. Thanks for the introduction, and thank you to all the organizers for inviting me to speak. So, as Laksha just said, this is the title of my talk, and it's also the title of a paper that we completed here at UPenn last month, and it was written in collaboration with Jonathan Heckman and Shitrang Mudia. So, this talk is going to be string theory motivated. Okay, I'm having some lag in the transmission. There we go. So this talk is going to be theory motivated, but not at all about string theory. Rather, it's going to sit at the intersection of holography and generalized global symmetries. And the key questions we wish to address are best motivated by recalling two slogans from each of these subfields. So the holography slogan I would like to recall is that if we're giving a boundary CFT, semi-classical gravitational dual, then we expect that any operator of this CFT should have some gravitational bulk counterpart. And the generalized symmetries is simply that by now we understand very well that the symmetries of a quantum field theory should be understood via their topological operators. And so putting these two things together, natural questions arise. So if we're given a CFT which participates in holography, and we're given one of its topological symmetry operators, what does this operator pull off to into the bulk? Does it pull off? Is there such an object, and what are its properties? So we know the answer to this question very well in the context of string holography in a large class of examples. And this goes back to work of Fabio, Ibu, Federico, and Sakura, and Iñaki that demonstrated that these topological operators, string engineered setups, come to life in the gravitational bulk as branes. The original topological operator is realized as the topological subsector of the brane. And this idea has been explored further by the group at Hopkins, and there's been follow-ups at Oxford, and there have been more works since. And so the general expectation that one might have is that this holds true more generally. Given a topological operator that of a C with a semi-classical gravitational dual, it should have a bulk counterpart which is some dynamical extended object. And the goal of this talk is going to give a bottom-up explanation of why this should be true. And we will not make any reference to top-down constructions. So in particular, there's going to be no string theory allowed. And one consequence of topological operators having bulk counterparts, which are dynamical non-topological objects, is that there'll be a no global symmetries theorem proven for, in this case, gravity theories and asymptotically ADS space. And it is via this no global symmetries part of our work that we connect most straightforwardly to the literature. And so I want to begin by reviewing some of the milestones in this direction, and then explain our reasoning from there. So having laid out this introduction, let me pause for a second to see if there are any questions about where we're heading. Okay, so the paper I'm going to review, and this is going to take some time, is titled Global Symmetries and Quantum Field Theory and Quantum Gravity, and was written 2018 by Harlow and Oguri. So the reason I've decided to review this paper is because first, it's very well known, closing in on 400 citations. And when we were circulating our draft, it was very often asked to put our results into relation to this piece of work. Another reason that it's useful to review this paper is it is the first work that I know of that introduces the very deep notion of subregion duality into the study of global symmetries. And so this will also be the working horse in our argument. And so it's good to review it, which I'll do in this. So I'll have to review it anyway. And it's good to see it work in this context too. And then the last reason this paper is useful to review is because they prove a no global symmetries theorem. And we would like to get a very similar result, but now extending it to non-invertible symmetries too. So the statement that they prove in their paper is that no quantum gravity theory, an asymptotically ADS space, which has a global symmetry, can be dual to a boundary conformal field theory. And they prove this via a proof of contradiction by showing that if one assumes to have a global symmetry in the bulk, then this is incompatible with properties of holography. Let me also say that in reviewing their material, I'm going to restrict to invertible zero form symmetries. And overall, I'm going to restrict to conformal field theories in dimension 2 or larger, with bulk systems in dimension 3 or larger, to avoid some issues with ensemble averaging. So their paper is rather long and contains many different perspectives, lattice, algebraic QFT. But here I'm going to focus on the minimal content that's necessary to argue their statement of no global symmetries. And in reviewing their proof, I've decomposed it into 4 steps, which I'm going to discuss individually, but let me start with the bird's eye perspective of how the argument goes.
So I can ask you a question.
Go ahead.
When they talk about quantum gravity in ADS space, are they now fixed topology with like ADS boundary at infinity, or are they supposed to sum over topologies?
Fixed. Fixed.
Topology. Okay.
I'll say this in a second too.
Okay. Thank you.
Okay. Okay. So here's the picture in step 1. So I've drawn the cylinder is ADS in global coordinates. Sigma is a spatial slice. Partial sigma is its asymptotic boundary, a spatial slice of the CFT. And so the starting assumption for the proof of contradiction is that we're given a bulk operator, local operator phi, and we assume that there exists some global symmetry which acts on it. Now, one needs to be precise what one means, and they are. And then using properties of holography and the definition of symmetry that they give, they map this bulk problem onto a boundary problem. And so they managed to reformulate it completely as this boundary statement over here, where the bulk local operator phi is replaced with its dual CFT operator O, and the symmetry is now fully expressed as some unitary operator acting on the CFT. And so here I've tried to sketch, over here, I've tried to sketch what this is supposed to look like on the spatial slice. Because we're doing zero form symmetries, this operator is going to be supported on all of partial sigma, as indicated by the red squiggly line. Okay, the next step, now that we're on the boundary, lies in reducing to subregions of the boundary. And this is what I've indicated down here. So the spatial slice of the CFT is decomposed into multiple subregions, R1, 2, R3, and R4, with the goal of similarly decomposing this operator. If a symmetry can be decomposed in this way, it's called splittable. and the symmetries that they prove their no global symmetries theorem for are splittable. And so using the split property, we can go from just, we can restrict onto subregions of the boundary. And then the final very deep step in their argument uses entanglement wedge reconstruction. And roughly what this says is that if you're given operators supported on one of these smaller regions R, they can only reach back into the bulk of with finite depth. And so this is what I'm indicating here with the blue shaded regions. And the contradiction now comes about that one can arrange for the configuration that I've sketched here. One can start step 1 with an operator phi, which is deep in the bulk, and assume there's a global symmetry acting on it. And then by the time one has stepped through these 4 steps, one sees that the global symmetry could not have acted on it at all, because it can only act on things in the union of this entanglement wedges, and therefore one has arrived at a contradiction. Okay, but it's worth revisiting these 4 steps in turn, and where improvements or alterations can be made to broaden the statements. So the first step lies in setting up the problem in the bulk. The bulk is a theory of gravity. So we have coordinate transformations, and we also have boundary conditions. So this goes back to Andreas' question. So the boundary conditions are such that the metric needs to asymptote to ADS. So we're in asymptotically ADS space. And then the diffeomorphisms come in 2 types. There are bulk diffeomorphisms, which taper off to the identity at infinity. These are going to give gauge symmetries. And then there are coordinate transformations which taper off to isometries. This is going to give the SOD(2) of the CFT. So if we want to talk about local operators, which are supposedly acted on by the symmetries one wants to exclude, then one needs to demand at least the following. Physical local operators, they need to be invariant under these bulk diffeomorphisms, gauge symmetry, and they need to be in representations of SOD(2). So this invariance under bulk diffeomorphisms forces one to introduce a gravitational dressing. So if the bulk operator phi transforms with respect to the gauge symmetry, then one attaches to it a Wilson line built from Christoffel symbols, whose job roughly is to replace a bulk tensor index by a boundary tensor index, right? Because the Wilson line connects to some boundary point X. And then the overall combined object is going to be gauge invariant and can be talked about as a physical operator. Okay, so given these local operators, Harlow and Uguri introduce internal global symmetries as, well, transformations which act faithfully on these gravitationally dressed operators phi. They also require that they preserve the boundary point X, because they want internal symmetries, so not the conformal symmetry group. Should not overlap with the conformal symmetry group. And then there's a whole bunch of other requirements that list out. Needs to commute with the boundary stress energy tensor. It needs to admit a representation in terms of unitary operators in the CFT. It needs to act locally with respect to the operators, which means that if I'm sending phi to phi prime, both these need to be dressed by the same gravitational Wilson line. And then there are additional requirements that they're imposing. And this is a long list, which is very intricate. But the gist of it is that the definition is made such that following statement holds. A global symmetry, in their sense, of a holographic asymptotically ADS quantum gravity theory gives you a global symmetry of the conformal theory. And so there are a number of comments that one can already make, given the detail of the definition, it's not clear how to extend it directly to p-form symmetries. They do address p-form symmetries. The way that they do is they note that if you compactify down p-form symmetries sufficiently often, get a zero-form symmetry, and that zero-form symmetry that they exclude, but there's no direct argument for a p-form symmetry. And even worse, it's not clear how to approach non-invertible symmetries in the framework that they lay out. So this is something that we're going to return to. Okay, but the definition that they laid out is such that their proof works. And the next step in their proof is to retreat onto the boundary.
Sorry, another clarification. The topological operator in the bulk is codimension 1 or codimension 2 in the bulk?
So this is the next thing. So it would have to be codimension 1, right? But the way that the proof is set up, and so this is what I was going to come to in 30 seconds, is that they completely avoid the discussion of what of this topological operator should be. And I think fundamentally the reason for that is because, well, they prove in the end that these things don't exist. So it's very hard to characterize them in the gravitational theory. So in short, well, it should be codimension 1. But in their proof, this is not addressed and it's not necessary to work. And then addressing it is not a necessity for them.
But I'm a bit confused because if it is codimension 1 in the bulk, then when you push it on the boundary, it's space filling.
Okay, this is going to be part of the resolution.
Okay.
Okay, yeah. So I'll come back to you when I address that point, and then we can check if it's fine with you. Okay. Okay, but for now we're completely avoiding the discussion of topological symmetry operators, and so this is also going to be part of the result that I'm later presenting. That, well, there is a bulk dual of the boundary object, but it's not going to be a topological operator. And so it can't be talked about in this context here of just considering symmetries. Okay, so in retreating onto the boundary, what they do is they take their bulk operator, they take the correct one parameter family of conformal transformations, and they map it onto the point that the gravitational dressing attaches. Taking some correct scaling, you get the dual operator and the CFTO. And then by the way that they've defined their symmetries, one can now describe the problem purely in terms of CFT data. So there's some unitary operator on the boundary of the CFT, which realizes the symmetry on O. Okay, and we've discussed the comment. So this avoids the discussion of symmetry operators. This is also something we will return to. The next step in their proof relies on the splittability property. And the job of splittability is to go from the boundary to subregions in the boundary. And the motivating example for why one might hope this to be true is of course, symmetries built from Noether currents. If I have a unitary operator U, which is the exponentiation of some Noether current over the boundary partial sigma, then simply decomposing partial sigma into this union of RKs, as I've drawn over here, gives you a decomposition of the symmetry operator, right? Trivially rewriting the integral then gives you this product structure over these smaller operators, which are supported on these segments of CFT space. And so they push this idea as far as they can push it. They introduce this definition. They say a global symmetry of a quantum field theory on this spacetime is splittable on M if for every open spatial subregion R, so one of these segments above, there exists a unitary operator V such that if I take an O, which is in R, and I act on it with this V, then it acts exactly as the original symmetry operator does. And if the O is outside of the support of V, then V doesn't act. And this definition is somewhat unpleasant for a few reasons. First of all, split property is something that depends on the spacetime that one chooses. There are examples like the invertible unbroken ZNF symmetry, as left unbroken by the ABJ anomaly, which is not splittable on certain M. So there are very well-known invertible examples which are not splittable. And it just so happens that in the spacetimes that are relevant for their proof, that on those spacetimes, all the symmetries they consider are splittable. And then a second feature of this definition, which from a modern perspective is a bit uncomfortable, is that these operators on these smaller regions that they propose are necessarily not topological, right? If they were, then I could just shrink them away and I would have nothing left over. So they need to be not topological, and so it's a bit uncomfortable to talk about symmetries from this non-topological perspective. Okay, but let's press on and talk about the key player. And this is entanglement wedge reconstruction. And this is something I'm going to review in ADS. It works a bit different in asymptotic ADS, but the statements I'm going to give later on work fine. So the starting point in discussing entanglement wedge reconstruction is the extrapolate dictionary. Right, the extrapolate dictionary is the state if I consider a bulk correlator of fields phi inserted at points x1 to xn at some fixed radial coordinate z, and I then take a proper rescaled limit of z goes to 0, then I land on a CFT correlation function where phi has been replaced with the CFT dual operator O. So this extrapolate dictionary is very useful for computing correlation functions of bulk correlation functions which are close to the boundary. One can get scaling behaviors and so on, but it's not as powerful for computing things deep in the bulk. And this problem of going a bit deeper into the bulk is solved by HKLL reconstruction, which was introduced in 2006. And so the statement, let's keep this, the statement of HKLL reconstruction, this is in the context of ADS, is that if I'm given a bulk operator phi, then I can reconstruct it from boundary data. And the reconstruction formula looks like this one. I have an integral over some domain on the boundary, and the integral is over some smearing kernel, and I'm smearing some CFT operators O. And the reason one might expect that such a formula exists, or how it's actually derived in this case, is that, well, one starts with the observation that the bulk phi needs to solve the bulk equations of motion. That's a PDE problem. This PDE problem has boundary conditions. And these boundary conditions can be formulated using the extrapolate dictionary. That's why the O's appear. And this PDE can be solved using green function methods. And that's why we have this expression like this. Okay, and let's make explicit what this domain of integration is. So the bulk support, sorry, the boundary part that the S of x that I'm integrating over is this green shaded region on the right. And it's determined as follows. I take phi, I consider its future light cone. This gives me this upper circle. I do the same thing for a passed light cone, gives me this lower circle. And then everything in between on this slanted cylinder is what's being integrated over. Okay. So this HKLL reconstruction works very nicely in ADS, but it relies on the existence of these green functions and that methodology. And this can fail in general cases if there's a black hole in the bulk, for example. And so to push past these limitations, one needs to improve HKLL, and this is what then leads to some notion of entanglement wedge reconstruction. Okay, so now I next want to explain how to improve HKLL to give what's going to be called Rindler reconstruction. So there are a few ways to improve it. So, well, there are two things in this reconstruction formula. Can't see that. There's the smearing kernel, so we can hope to improve there. And then there's the boundary data, so we can hope to improve there. The first step lies in improving the domain of integration and the boundary conditions. We can reduce the domain of integration to a single spatial slice. So this is the white circle in the figure up here and also in the figure down here. And this is simply achieved by time translating the operators OX onto a common spatial slice. Okay, so this gives us some complicated expression in terms of just these operators, but it can be done in principle. And so I can write a formula very similar to the above, just using with the integral just running over the one spatial slice. So I can bulk construct operators from exactly one time slice. Now from here, Rindler reconstruction. Let's try and keep this. Rindler reconstruction makes a stronger statement. It says that I can reconstruct bulk operators, again, with a very similar formula as above, phi, only using this arc R in white here. And I can reconstruct it whenever it's in the entanglement wedge of R. So now in ADS, what is this entanglement wedge? So if I take R, and so that's a boundary region, and I consider its domain of dependence, so that's this causal diamond. So it starts at the boundary, it goes up on the boundary, it comes back down to the other end, and it sweeps out something similar on the other side. Then if phi is okay, then given this diamond, I can shoot light rays into the bulk, future and past. And their intersection is going to be this wedge, which I've shaded here in golden. And if phi is inside of this wedge, then I can reconstruct it with an integral of the above form, where the domain of integration is just R. And this is a very powerful statement because it's an example of a subregion duality, where I'm taking a subregion of the bulk and I'm reconstructing, the boundary, and I'm reconstructing a subregion of the bulk. The motivation for why this might work is given here by following observation. The Green's functions, which were used in the bulk reconstruction, turn out to not be unique. And so there is some shift one can do by other functions. And you can modify your Green's function. In particular, you can modify it to kill off its support outside of this region R if you're trying to reconstruct such a phi. So overall, we have some expression like this one here. So we have some expression like this one here. We're only integrating over this small boundary subregion R, now instead of Sx. We've modified the smearing kernel, and we've modified the boundary data too. Okay. So the key consequence that Harlan and Guri use is that, right, they have these small operators supported on these smaller regions. And by this reconstruction technology, they can only implement global symmetry transformations on bulk operators in these entanglement wedges. So, right, one sees where the contradiction comes from. Right, let's go back up. Decomposing, sorry, we're over here. Decomposing, if we can decompose our symmetry operator into these small pieces, then we can argue by reconstruction that they cannot reach fully back into the bulk. Okay, so this completes my review of their argument of why there are no global symmetries by their definition in asymptotically ADS space. And so let me pause for a moment to see if there were any questions, and otherwise I would press on with content of our paper. Okay, so as Andrea pointed out before, how should one think of the what one would call the symmetry operator of the global symmetries that we've just didn't show that existed? Or maybe phrased slightly differently, what is the bulk dual of a topological symmetry operator of the boundary CFT? And another question is, how can we prove no global symmetries in asymptotically ADS space, more generally including non-invertible symmetries? So now the more modern starting point is, so we'll start in the CFT, and we'll have some topological symmetry operator N, which I've schematically written like this. It has some, it's supported on a submanifold Y. It has some TFT living on it, as characterized by this Lagrangian say, and then there's a path integral over the field of the TFT. I'm going to denote the symmetry action of N on an operator O as sending O to the superscript N. Okay, and then what we've just also learned from in the bulk, we have also the bulk reconstruct O tilde of X comma Z. And this is given by this smearing expression. So these are the pieces of data which I've tried to put into this image up here. So on the boundary, we have O, which now need not be point-like. We have N, correct dimensionality to link O. And then there is the bulk reconstruct of O tilde. Okay. Now, one would, of course, want to just draw the same thing for N tilde, for N and N tilde. And so this is one way of phrasing the question. What's the bulk dual of N? Does something like N tilde exist? And if N tilde exists, is it topological? And so here is a helpful comic to think about the situation. So in the above picture, right, Z is a coordinate going radially inwards. And so I can think about smaller and smaller cylinders at constant Z. This radial direction corresponds to energy. And so this foliation of the problem is sometimes also referred to as holographic RG flow. So here I'm drawing the configuration at Z equals 0. I have my symmetry operator linking O. Now, if I move a bit deeper into the bulk, let's assume for the moment that N tilde exists. Then this is the picture I would draw. We will show that in a moment. Both N tilde and O tilde smear. But if I'm only going not too deeply into the bulk, then they only smear a little bit, and the length scales I have access to are enough to still distinguish these two objects individually. But if I continue pushing deeper and deeper into the bulk, at some point, I have lost the resolution to distinguish N tilde and O tilde. They get smeared together. And the thing that one sees then is the bulk reconstruct of the symmetry transformed operator, O tilde and O tilde superscript N. Okay. And it is this picture similar to it that we're going to analyze deeper momentarily. So let me first make some comments though. So this goes back to Andreas' question. So first of all, what's the symmetry action? O tilde and putative N tilde. So these link for every value of Z. And okay, they link for every value of Z. And the reason that this is not in contradiction to the SymTFT expectation one might have, where charged operators extend by one additional dimension and charge operators just pull off with in a dimension preserving way, is because in ADS-CFT, the full bulk, right, is dual to the conformal field theory on the boundary. So by matching colors, one should think of the full bulk as the physical boundary condition. So we're not moving in this additional direction that is postulated by the SymTFT. And so there is no contradiction to that expectation because it's a different situation. Then a second comment to be made is that what we've learned from the entanglement wedge reconstruction and of the subregion duality is that this Z star, the point where O tilde and N tilde smear into each other, is at finite depth. And right, this is again the comic which demonstrates this. If I'm on the boundary and I start with my O and N in the CFT, and I now bulk reconstruct, then there is a finite distance Z star. That's bad coloring. Z star, where I can no longer distinguish these. And so here is just a picture drawn from the perspective of the local operator O. And so O tilde is going to transform into O tilde of N past Z star.
Max, sorry, I have a question. So maybe I missed something. So at the boundary, N is a topological operator. Then
yes.
The surrounding of O shouldn't matter. So I can push N very close to O or make it very large, doesn't matter. So that's how can Z star have an intrinsic notion? So if I start with N surrounding infinitesimally the operator, I expect that the Z star will be very close to the boundary. While if you, I mean, what am I missing? It seems that there should be any intrinsic notion, right? Since at the boundary N can be moved that way.
So, correct. So these, yeah. Okay. Let me see if I understood your question. So I'll say something, then you can comment again. So this Z star is indeed dependent on where I put N, because I need to draw the correct region from which I'm going to do reconstruction with. And if it's a bigger region, it's going to reach deeper into the bulk, and so the Z star will be larger. And it is correct what you say. I can also pinch N, right? And so in the right picture, if I contract N onto O, then I would just have over here just a single purple bulk reconstruct. Okay. So given that, does that answer your?
Yes. I thought that was intrinsic. Yes, that answers my question. Yes,
sorry, it's not intrinsic. It depends on yes, your reconstruction.
Okay.
Okay. So now I want to give the main claim and the argument for it. So here, right, in the picture we just discussed, I've avoided to draw an N tilde. And so now I will argue that N tilde exists and that N tilde is not topological. Okay, and the argument goes as follows. we want to compare two configurations. So here on the, let me remove this. Here on the right-hand side, the simple of the two configurations, where we've just inserted O in the CFT, and we're doing a bulk reconstruct of it. And so we have just a unaltered O tilde profile just being reconstructed into the bulk. So that's the, what do you say? That's the control. And what we're comparing it against is the situation where we have the O and the symmetry operator. So from what we've just discussed, so it was a very good question, is, right, if I shrink n onto O, then I expect this left-hand figure to basically just have this purple, the bulk reconstruct of the symmetry transformed operator. And in the other limit, if I make n very large, I can consider a small region which just contains O and bulk reconstruct from there. So I know in that situation that I would have a situation where I first, for sure, have a red reconstruct. And because these two limits I can smoothly interpolate between the two, I know that I have to have something where I have this transition region. And then by general arguments, it needs to be around Z star. Okay. Now, if there were no object n tilde, right, then I would, on this picture here, I would start bulk reconstructing. I'm solving my equations radially inwards, as we discussed in the bulk reconstruction. The moment I go away from the boundary, I've forgotten about n. And so I would just be reconstructing O tilde. So the fact that I have this transition region already tells me that there needs to be some object in the bulk. So this is not particularly shocking. This is just saying that the ADS-CFT dictionary is working. For every boundary object, there should be something in the bulk. The more important piece of data to argue for is that n tilde is not topological. And the way that this is argued for is that if n and n tilde were topological, then the left-hand side would only differ from the right-hand side by additional topological data. And so in particular, the stress energy of the two configurations would need to be the same. But the stress energy is not the same, because in this transition region where O symmetry transforms to O tilde symmetry transforms to O tilde superscript n, this could be as simple as a phase rotation. There are derivatives in the fields, and these derivatives introduce stress energy, what I've written out over here. And so we immediately arrive at a contradiction. And so the assumption that n tilde was topological was wrong, and so n tilde is not topological. And so these are the key statements that we want to make in our paper. And so, because this is, let's say, the take-home message, these bulk objects n tilde exist and they are not topological. Let me also pause here quickly to see if there are any questions. So what we're arguing now is that whenever we're given a symmetry of the CFT, there should exist some extended dynamical object in the bulk. Right, so that's the correspondence that's being predicted. Okay, so this proof is a existence proof. And so we don't know a lot about the properties of n tilde, but we can try to parameterize our ignorance. There is, of course, the first constraint that this bulk, let's call it brain, needs to satisfy is that in the limit of z goes to 0, in the limit of z goes to 0, it reduces to the topological symmetry operator. Sorry, the program crashed.
Sorry.
Yeah, go ahead.
While you fix this, just to be sure again, this n tilde now is supposed to be codimension 1 in the bulk.
Sorry, the n tilde is going to be codimension 2 because it links with the object in every constant z slice.
So it cannot link with O tilde.
it links if you restrict yourself to a constant Z slice. It's like you're considering, right, consider Z as the energy scale of your field theory problem. And then you get like a snapshot of your field theory at different points along the RG flow, and the linking is in these snapshots.
Okay, but so this I think automatically proves that until is not topological. Because if it links at any fixed Z slice, if it were topological, you can unlink it going in the bulk. Going out from the Z slice. I mean, if it is topological, it does not have the right dimensionality to link. So if it links it and does something non-trivial, it must be non-topological.
Yeah, I mean that's I think that might be a bit quick, but I mean in a sense you're right.
Okay.
Sorry. Okay. So, right. Thanks for the question. Right, and so I was just slowly coming to a conclusion. So I wanted to state some properties of this brain that we're predicting. So the first constraint is that if we move it back onto the boundary, it should reduce to the symmetry operator of the CFT. And so this requires this object to have following form. There is some vector out front Z, which I'm going to address momentarily. Then there's the TFT part of the symmetry operator that needs to hang around here. And then there are some non-topological terms which are going to be turned off in this limit, but they are relevant in the bulk. And so this vector Z is, so what could happen is that, well, I guess this goes back to Andreas' question too. It's not guaranteed that when you, I think there are cases where when you pull it off, there might be something attaching back to the boundary. And so this is what we're parameterizing with this Z, the possibility that this might happen. So one thing that we can already say is because the topological sector of n tilde is determined in this limit, this is something that we can compute from the SymTFT. And so here's a very simple example for a U10 form symmetry, which one has gotten by okay, good. Which one is gotten by some integral over a current. Then this U10 form symmetry is going to have some background field A1 in the CFT. That thing is going to have some gravitational dual. This is going to be the A1 field. I can build the F dual. Right, this is just start the A1, and this is going to describe the topological sector of my n tilde. And by these equations of motion, right, I can argue, this is just some Stokes, that in the limit I'm reproducing the correct symmetry operator. So for just analyzing the topological sector, well, okay, this is no surprise. The symmetry TFT and the data of the CFT is completely sufficient. So what can we say about the non-topological part? Okay, again, we just parameterize our ignorance. So we have this extended object, which I'm calling the brain, and here's its action. It's going to have some unknown world volume tensor, right? If this M were a D brain, then we would have the pullback of the metric, an NS2 form, and some gauge fields living on it. But in general, we don't know. And it's a very interesting question to ask. Well, how might one analyze properties, in particular the field content of these extended objects, or the world volume fields of these extended objects? Okay. And then here are the topological terms we just discussed. Then out front is the tension. And there are some bounds that one can put onto the tension. On dimensional grounds, it should go like 1 over some characteristic length scale. And this length scale can be interpreted as the Compton wavelength of this extended object. So from this interpretation, we know that it should be much smaller than the ADS radius. And this is because if it were of similar magnitude, then as soon as you move it off the boundary, it starts fluctuating, spreading everywhere. And because we've seen that this rate of smearing is controlled by the entanglement wedge reconstruction, and because of this takes some time, this cannot be. So this characteristic length scale needs to be a lot smaller than the ADS radius. And then another thing one can say is that it needs to be larger than the Planck scale. And this is because we've predicted the existence of this object using the effect description of the semi-classical gravitational dual. And so it needs to be valid in this framework. And so we can bound well, the length scale of source of the tension above and below by the Planck length and the ADS radius. So it's a future work of ours. We're going to explore in greater detail what one can say about these extended objects. But let me not comment on that now, and simply give a very brief summary of the things that I've told you about and other things that are in the paper that might interest you. So the two key takeaway messages are that this gives a argument for no global symmetries and asymptotic ADS. Because if we had such a symmetry, there would be a topological operator. You could bring it to the boundary. Then using the arguments from before, you would pull it off and you would see that it's not topological. So this now immediately applies to non-invertible symmetries. And the second statement is that for topological symmetry operators of the CFT, by the above arguments, we are predicting that there is some extended brane in the gravitational bulk dual. Okay. So there are other things in the paper that we discuss. So -1 form symmetries are one of the things. So these are space-time, the topological symmetry operators are space-time filling in the CFT. And so it's not quite clear what one means if one wants to, well, smear these as one moves them into the bulk using reconstruction, but analyzing things more carefully, very similar arguments work, and one can exclude these. And then there are also very natural question of what we want to call lower form symmetries arises. Because one can ask about, so what about -1 form symmetries of the gravitational dual? Are they allowed? And from the perspective of the CFT, these would be -2 form symmetries. And so we discussed this notion of lower form symmetries exactly in a context like that, where we say that if you have a system, more generally, it's a, let's say, a QFT within a larger QFT, then you can introduce this notion of lower form symmetry by saying that, well, a minus form symmetry in the ambient space should be interpreted as a lower form symmetry of the defect theory. And then another thing that we address in the paper, which I haven't written out here, is that we return to this idea of splittability that was instrumental in Harlan Duguri's proof, and comment on how this should be approached in the case of non-invertible symmetry. There, because there's a TFT on the world plane, right? As soon as you start cutting it up, you're going to get edge modes, and you could need to deal with these. So this is something that we also discuss. But okay, I'm a bit early, but nonetheless, let me thank you for your attention. And if there are any questions, please let me know.
Thank you, Max. Yeah, please go ahead and ask questions.
I had one. Hi, Max. Thank you for the talk. I had a question. Do you have any understanding or idea of how the fusion of two of these n tildes is supposed to work in general? Or is this something you can use to constrain the form of these non-topological terms?
So the topological, I mean, okay. When you say fusion, okay, I guess you have in mind fusion of topological operators. So there's the first question of how would you want to extend fusion to now these non-topological operators? I mean, we were struggling to describe their non-topologicalness to begin with, right? This was only an existence proof. So at the moment, the answer to your question is no. But well, just the topological part fuses exactly like you know, and this is already discussed in examples in the string holography cases by Sakura et al. And Iñaki.
Okay, thank you.
Another question to match this discussion with the usual. I mean, in holography, typically we say that if you have a global symmetry on the boundary, you will have a gauge field in the bulk. So I would like to understand what's the relation with your n tilde. Maybe I mean I can suggest a kind of intuition that I have, then you can tell me whether it's correct or not. You have this gauge field in the bulk, so you can construct Wilson lines of this gauge field out of this gauge field, and you will have Guko-Witten operators in the bulk, which measure the holonomy of this Wilson line, and those are codimension too. So maybe I can think about this n tilde as this Guko-Witten operator, which however are non-topological because in the bulk the Wilson line can end on some operator. So this Guko-Witten operator which links with this Wilson line must be non-topological. Can this be correct?
Yeah, this is correct. So okay, I think I did a bad job of explaining, but this is roughly what happens in this little example.
In the U1 case, I see.
Here is exactly this codimension 2 operator that you are mentioning. Okay, I've made a mess. Let me clean it up. Right. This guy, the F dual, is codimension 2, and it's exactly measures the Wilson lines you were just discussing. So yeah, that's the correct intuition.
Okay, so in a certain sense, you have a construction of what is n tilde. Even, I mean, at least for invertible symmetries.
In this case, yes.
I see.
Yeah.
Okay, if there are no more questions, let's thank Max again, and thank you very much for